masters as far as I read today. He did a master of science in 2007, and then he did a master on philosophy 2 years later. After that, he obtained a doctorate, a PhD degree in material science from, also in India. Bachelor, master, but to master, doctor, PhD in India. And then he worked there for 4 years. And after that, he joined UNAM as a postdoctoral fellow. So he joined ICF in 2015, right?
Yeah.
Then he went back to India and come back as an associate researcher in ICF. So he is kind of brilliant scientist. He received, for example, some awards already. He's very young. He received, for example, a Young Scientist Award in 2012 from Indian Chemical Society. And also he received Best Researcher Award in 2013 from his university, VIP University. So as you can see, he's kind of brilliant. You can hear a very nice scientist with us. So welcome, Kumar. Thank you for accepting participating in the colloquium.
Thank you, Victor. So thank you, Victor, for your wonderful introduction. So thank you all for all presented here. So today I'm going to talk something about the research works which I did in past and which I'm doing currently. Okay. So the topic is the nanomaterials and nanofibers for energy and environmental applications. And there is a tagline, right? Are we close to achieve sustainability? So, what is sustainability? What is sustainable development? So, here the development that meets the needs of the present without compromising the ability of future generation to meet their own needs. So, whatever the facilities we have or whatever the resources we have, we want to safeguard it for the current generation. And we want to safeguard the whatever the resources we have for the future generations. So, in the sustainable development, mainly I am going to talk something about water, which is an essential for each and every person and a lot of human beings, including. And then I am going to talk something about energy, but I didn't talk a lot about energy conversion, solar energy conversions. But we are working currently on production of hydrogen using solar energy. So first, if you look at why we should do something related to water research. Okay, so still today, as per this is the statistics from UN, United Nations. So there are total of 748 million people still don't have access for pure water, and whatever the existing indicators, they do not address the safety and reliability of the water supplies. So, to meet the requirements that everybody should have safest drinking water, so we should do something for future generation and for present generation to have an access for pure water. And the second thing is the solar energy. The increase in industrialization, and many industries are coming up, and it is expected by 2050, whatever the actual energy requirement, what we have today, it is going to double. It is going to double in 2050. We need more energy requirements. And finally, talking about the hydrogen fuel, which is the fuel for future. So, with the introduction of fuel cell technology for zero emission vehicles, this hydrogen revolution starts actually, which offers the sustainable solution to our nation's energy and the climatic challenges. So, what hydrogen can offer? It offers energy security. We don't want to rely on other countries to import any foreign oils, right? For example, many countries rely on Arab countries to get the oil. And then hydrogen production technology can potentially take advantage over the current renewable resources like solar, wind and geothermal and climatic change. The most important thing, vehicles produce near zero carbon emissions. In sense, like there will be no emission if you are using hydrogen as fuel. So, for example, now many of the cities were contaminated with a lot of carbon dioxide, carbon monoxide, and it is a biggest problem. If there is enough commercialization in making use of hydrogen as fuel, there will be zero emission for sure. And then with zero emission, what will happen? The urban air quality will increase. And then economic vitality. So any nation can secure the share if they are pioneered in the fuel cell technology or hydrogen production technology for sure. So starting my talk with water purification. The first here I'm going to start with NZVI, which is nano zero valent iron. So what is nano zero valent iron? The elemental iron in its zero valence. And people can ask, see, the stable states of iron is +2 or +3, but why zero valency? It has its own applications in water treatment. So it's a versatile material. So how to produce this zero valent iron? You just take any salts of iron, it may be a ferrous salt or ferric salt. You just treat that with enough stoichiometric amounts of sodium borohydride. So this sodium borohydride being a good reducing agent, it will reduce iron to its zero state. And this zero state is highly unstable, and it is as dangerous as sodium. But it has its own applications in water treatment. So how to produce this? So just take any salts of ferric chloride and you just supply using a peristatic pump, and you supply sodium borohydride into it. And there are many factors which influences the size, the properties of zero valent iron. So that includes the reaction time, temperature, and the amount of stoichiometric amounts of sodium borohydride and stoichiometric amounts of ferric chloride, and the pH values at where we are doing, and the mixing speed. So here, since this is an exothermic reaction, it is highly recommendable to do this reaction in a cold chamber. So looking at the zero valent iron, as I told you, if iron is in zero valency, this tends to convert into its stable form either to Fe2 plus or Fe3 plus very fast. If you take the bare zero valent iron, if you just subject it to oxygen or you just put it in oxygen, it will immediately ignite and convert into either ferrite or magnetite. So that's a problem. But if you control the process parameters, you can able to at least manage the zero valent iron with a shell of iron oxide or iron oxyhydroxide at least. And thus the formation of a shell on zero valent iron, it is a good thing or bad thing, we'll discuss it later. But concerning only zero valency, we have this: the zero valent iron, when subjected to any water that was contaminated with metal ions. For example, any zinc, cadmium, lead, these are all very dangerous metal ions that present in water. A lot of industrial effluents that contains water. What happens? So it is a general thing when a metal comes in contact with other metal which is having two different reduction potentials. What will happen? Local galvanization will happen. Local galvanization will happen, and one will behave as anode and the other will behave as cathode. So anode just gets corroded and the cathode gets reduced. So this is what is going to happen. But here, based on the cell potentials of the zinc, if the cell potential is negative and the half cell potential or cell potential of iron to Fe2 plus to Fe0 is -0.044, and if it is very near to the cell potential of iron, so the absorption or surface compensation takes place. Upon increasing the cell potential, it may reduce, and reductive precipitations also takes place. Now, one thing, if it is a bare zero valent iron, it can do only one work, that is, it will always try to donate some electrons and go to its stable state. Only reduction can be taken place. But if you have a shell of iron hydroxide on it, both reduction takes place, oxidation takes place, and adsorption also takes place. So this will be very good in increasing the efficiency of decontamination of water. Efficiency of decontamination of water. So you can see from this, even starting from metal ions on the surface and onto the zero valent iron, the different processes are occurring in decontaminating the water. So what we did in this particular area, we studied the interactions of groundwater arsenic. Arsenic is a deadliest species in the water, and both arsenic 3 and arsenic 5, these two guys are very bad for, and many of the, even in Mexico, many of the sites were contaminated with arsenic. So we studied an interaction of groundwater arsenic with the zero valent iron. So what we achieved here, we developed a method to at least bring an stable zero valent iron, and then we just under anaerobic conditions we try to check the adsorption capacities of arsenic 3 and arsenic 5, and we try to bring out the exact mechanism behind how they are getting decontaminated. And the third thing is, using the same zero valent iron, we control the larva. You know, the before stage of mosquito, there is a larva, and we even control the larva from water, and we tested against the mosquito larvae also. So in brief, we synthesize the zero valent iron, and one more thing, using sodium borohydride, there is a problem. We are going to generate a secondary contaminant, which is boron hydroxide. So it is not that good to use the sodium borohydride always, but one more best thing is we can use some other reducing agents. There are plenty of reducing agents, and if you can see, once you look at the US Environmental Protection Agency page, they are widely working on the zero valent iron for decontaminating the waters. So there are n number of methods where we can avoid the secondary contaminants. So we did some green chemistry methods to prepare this zero valent iron using hydrazine, or we can use sometimes polyphenols, secondary plant metabolites also to reduce the, and provided that the reduction potential should match. So don't think that all the zero valent we can convert with any of the polyphenols, we can convert any iron 2 plus to zero valent iron. It is not possible. We want to check the reduction potentials of both. So we managed to do the stable iron, and if you can notice this in high resolution transmission electron microscope, there is a core zero valent iron, and there is an outer shell. There is an outer shell which is iron hydroxide, iron oxyhydroxide. And since this is very thin layer of iron oxyhydroxide, you can't able to see that in XRD, so you can get only the peak of zero valent iron. So if you look at the arsenic removal capacities of this particular zero valent iron which we prepared, it almost in 100 hours it is possible to remove 100% of the arsenic in the water, but provided that if arsenic is in plus 5 state, and if it is in plus 5 state, it will take more time to get 100% removal. So what's the reason? Actually, this is the work for which we got I got the award from Indian Chemical Society. And here, if you look at what happens here, arsenic, if it is arsenic 3, it will directly absorb onto the surface. Or if it is arsenic 5, what is happening? If it is arsenic 5, it will directly absorb onto the surface. If it is arsenic 3, it will just oxidize to arsenic 5, and then absorption will take place. So that's why if you look at these graphs, you have the difference in absorption capacities of this zero valent iron. So after that, we thought the zero valency for area transportation. If you want to take that into the iron, if you want to do something with the zero valent iron, it is very hard to do that. Why? Because it ignites very fast in the oxygen atmosphere. So what we thought, we want to prepare some zero valent iron balance we can use. So here what we did is we used some iron stabilizers. So in order to cap the zero valent iron and avoid the aerial oxidation. So in this regard, we used three different, and we tested with a lot of polymers. is polyethylene glycol, thereafter is sulfosuccinate, and dimethylcaptosuccinic acid. These three stabilizers, they protect the zero valent iron. After protecting the zero valent iron, you just take that and you put it in the air, nothing is going to happen for that particular iron nanoparticles. So we sterilize this using these three, and you can check the XRD patterns even after the 12 months. There is no change in the zero valent iron, and we didn't see any iron oxide peaks here. So this was actually a patent which was granted recently in 2017. So for this work. And coming back, so after arsenic, we tested the same zero valent iron particles in controlling the larva, from water bodies. So what we did, actually did this work in India actually. So we just went around the countryside and we tried to collect the larva, and we deposited this larva into the entomological centers in the respective cities to speciate what exactly it is. And after speciating, we got that these are two vectors, which is Culex and other one is subvectors. So these two are, the first one is malarial and the other one is malarial vectors. So we just try to control the vectors using this zero valent iron with different concentrations, and you can see the lethal concentration, lethal dosage for 50% species to die is 64.1 milligrams per liter, and then here 108 in the case of filarial vectors. So this with this zero valent iron, we try to control both the malarial filarial vectors, and we decontaminated the arsenic. Then later we thought there is a big problem with the zero valent iron. Once you disperse into the water, how to recollect it? Yeah, it is magnetically separable. Even if it converts into iron oxide, you just put a magnet, you just separate the particles. But it is okay for the laboratory scale. If you want to apply really into the people, it is not at all possible to remove the iron once again in the water. So what's next? And even what we patented that contains a sodium of polymer. Once we apply this into water, this polymer will create an acid, and this iron will come out and it will do its work. And once again, if I want to remove that polymer from water bodies, it is going to be exactly tough. So keeping all these things in mind, we try to incorporate the zero valent metals into polymeric fiber maps, nanopolymeric fiber maps. So why? You just take the polymeric nanofiber map, which was incorporated in zero valent iron, and you just put it into the water, do the absorption studies, and just take it. It's that quite easy. But before going to talk something about that particular work, I would like to talk what is nanofibers and how we are going to prepare the nanofibers. So we are going to use a technique called electrospinning to create the nanofibers. So when we are talking something about nano, it will have all the properties changes from the whole polymer, right? So we are going to get the fine polymers with the high surface areas, and we are going to get lowest porosities, and lot of properties are going to change. And it is easy to scale up this particular nanofiber process to industrial levels also. That is the beauty with this particular technique. So this technique actually started first observed by Raleigh in 1897, and long back. And recently, after Farnhall's patent, there is a huge number of works on these nanofibers, and it went up to starting this particular material in the commercialization in last 2 decades. Like Donaldson Company and Friedensburg Company, they are creating the masks using these nanofibers. So what exactly electrospinning and how to create the nanofibers? So we have electrospinning rough switch here, in which we have a syringe pump, and we have I can say this as a syringe, and then we have a current collector, and we have a voltage supply. So what exactly happens here? Just first, this particular process principles involves in subjecting a polymer solution or melt. You can either take the polymer and put it in a solution to desired viscosity, and the second one, you just heat it up to the melting point and you just prepare a polymer melt. You can use anything in this syringe. So, and on what solvent we are going to use, based on the solvent, the surface tension is going to change. Each solvent is having its own surface tension, of course. And if you apply electric field to this polymer get charges, and if you keep on increasing the electricity, what will happen? It will form a hemispherical surface at the tip, and if you keep on increasing the electricity, it will elongate in the form of conical shape, which we call it as Taylor cone. And once again, the electric field reaches the critical point. What will happen? The repulsive electric forces overcomes the surface tension forces, and this is the critical point where the charged jet converts into a solution is ejected from the tip, and it forms a fiber. So there are different regions in this particular zone. So see here, this is the Taylor cone what I am talking about, and this is the charged polymer which is coming out of this jet, and it will form after increasing the electrical field, the Taylor cone droplet become unstable and leading to a single fluid jet. This is the jet, and then it was triggered by the electrically driven bending instability, where this fiber gets splits into nanofibers. So it will deposit on a current collector. So this is what happened. So we are going to charge the polymer will form a Taylor cone, and if you keep on increasing the voltage, it will form the nanofibers. But it is not that easy as I am speaking, to form nanofibers. So there are various parameters you want to take care in order to get a particular nanofiber. As nanofibers is concerned, the diameter of the fibers and the defect-free fibers, and to collect the uniform fibers, it is very, very difficult. If you look at these two pictures, instead of getting a fibers, I am getting a fibers with spindles. And here, instead of getting a fine fiber, I got a porous fiber. So this is, each and every parameter is very, very important. What are the parameters that governs the nanofibers? So we have a lot of parameters. Solution parameters concerns viscosity, conductivity, and molecular weight of the polymer, molecular weight distribution, surface tension, polymer structure, and solution of the properties of the solution. And if you look at the process parameters, how much electric field you are applying, how much kilovolts you are applying to this particular polymer, and then tip to collector distance, and flow rate, hydrostatic pressure, and plate movement, and ambient temperatures like environmental, like humidity, temperature of the surroundings, solutions, airflow rate, everything is very, very important. So this is one of the experiments what was done in our laboratory. Can you find any fibers there? There is no fibers. So that is, actually we tried for fibers, but what happened? Because of less process control parameters, instead of getting electrospinning, we got electrospinning. So instead of getting fibers, we got the polymeric nanoparticles. So here each and every parameter is very, very important. Very, very important. And finally, Dr. Ivan tried to get some fibers. So he just found some fibers with the process parameter control. So here the process parameters are quite important. If you look at here, the process parameter is only concentration. If you are using the low concentration, you are going to get the polymeric nanoparticles instead of polymeric fibers. If it is intermediate, you are going to get the spindles along with the fibers, which is not at all good. And to have the desired fibers, you want to have a good control on the process parameters for sure. So if it is excess, you can get the action. Okay, fine. If only concentration is the problem, I'll keep the concentration same and I'll play with the molecular weights. If it is low molecular weight, once again I'm getting the spindles, and if it is moderate molecular weight, I'm getting very good fine fibers. If it is high, I'm getting instead of nanofibers, microfibers. So that's the problem. And then if you play some the parametric controls like the electric field which you are applying for the polymers, if you apply different electric fields, the polymeric size don't change that much, but there is a real change observed by few researchers actually. But there are a few different parameters which we want to have a good control, like flow rate, distance between the tip and collector, and the collectors. The collectors must be conductive, and then the ambient parameters like humidity, and always we should see how much moisture inside the electrospinning chamber. Everything is very, very important to have a desired nanofibers. And this is no more related to the energy and environmental application, but it is a quite important application of nanofibers, which is in the biomedical tissue engineering actually. So they will prepare the nano scaffolds, and they will just do the tissue culture into the scaffolds, and they will form the tissue growth, and they will implant the tissue. That is one of the major thing. And if there is any cuts in the any organs of the human body, right? So how to apply it? So I want to do in situ nanofibers. So, but the current color must be conductive in the case of electrospinning. So there is this, quite a development by Kendry and his group in 2017. What they did is they given a high pressure blow technique to form in situ fibers into the organisms. So if you have a cut in any part of organism, you don't want any current collector which need to be conductive. You just give a liquid jet, liquid nitrogen jet or gas with high pressure. You just put it give a sufficient pressure in order to convert the polymer into nanofibers, and it is being used for wound dressings also nowadays. And there are a lot of biomedical applications which I don't want to talk, and here is the environmental application. As I told you that Donaldson company and one more company actually they are being into this business. So here you can able to see the mask. The mask is from some other company, but the material of the mask is being produced by Donaldson company. If you look at this particular mask in the microscope, you can able to see the polyester spun fibers, and on the top you can able to see the nanofiber web. So what actually it does? It actually, if you wear the mask and after some 2 to 3 hours of usage, you can able to see a lot of small particles in the microscope onto the nanofibers. So it's a wonderful application in order to have a good control on our breath. But what we are doing actually in our laboratory, we got a project from College for water purification. Here what we are doing is we are trying to incorporate the zero valent metal, what I am talking before some time slide. We are trying to incorporate the zero valent metals into the nanofibers. The problem is to achieve a good control on the nanofibers, what we are expecting, it is very difficult. It is very difficult in this case. Sometimes the nanoparticles mesh. We can see on the top of the polymer, and sometimes into the polymers, and sometimes we can get the fine disperse. This needs once again a good process control. But there is a slight modification in the technique what we used earlier. We have a coaxial spin. Initially, we can able to see there is only one signal with a needle, and we are going to give a polymer, and we are going to have a polymeric nanofibers. But here, what we are going to do, we are going to use a coaxial spin with a dual jet. In one jet, we are taking the polymer with nanoparticles in the center, and the other one is only polymers at the outside. And then we will start doing this electrospinning. So we will end up with nanofibers something like this. So we have different types of coaxial jets as shown here. So this is the actual electrospinning equipment which we got from the project, and we have process control parameters in order to incorporate zero valent metal into the polymeric nanofibers. Yeah, that's a good observation from our team actually. So there are some classes of zero valent metals in this form. So we have a lot of process control parameters here which we can't able to see very clearly, but here we will get the fibers with totally encapsulated, and we'll get the fibers where the metals are partially encapsulated, and sometimes it is like partially holded in between the polymers. To have a good control, to get something like this partially encapsulated, where the polymeric fiber holds the nanomaterial, and where the nanometal surface should be available for another. So this is very, very important, and we try to create those type of things. And prior to testing this particular zero valent metal, that is zero valent nickel, We just tested with zero valent nickel directly itself, the removal of chromium, which is passenger. So what we did, we prepared as I shown in previous slides how we prepared the zero valent iron. In the similar fashion, we prepared zero valent nickel using sodium borohydride, and which is magnetically separable. You can able to see here. So you just put a magnet, you can able to remove the adsorbent, and then if you look at, we just tested with the adsorption studies with chromium. And if you want to analyze chromium, either you want to go for advanced techniques like atomic absorption spectroscopy or inductively coupled plasma optical emission spectroscopy. But since we don't have, we just went for a colorimetric technique. You just take diphenyl carboxide, which can make a complex with chromium, which will use various colors depending upon the content of chromium. See, after with the time, the color was getting decreased, which indicates that the chromium percentage is being decreased. So what happens? So within 5 hours, actually we almost achieved 98% of removal efficiency using this nickel nanoparticles, but this is without fibers. But then what we did, we incorporated nickel into the fibers. Then we did this test, drop casting test for to check whether the fiber is or hydrophobic or hydrophilic. So if it is hydrophobic, I can't use this nanofibers for water treatment applications. It should be hydrophilic. So within few nanoseconds, actually this water droplet got absorbed into the fibers. So that's the beauty, and we almost achieved 80%. But why there is a decrease in percentage of removal when compared to that of the earlier one? So here the dispersion of nanoparticles into the polymer fiber differs. As we are using nanoparticles, the efficiency differs. And here once again we tested up to 200 milligrams of nanofibers. Yeah, for sure we are going to get 100% of chromium reduction. So that's the beauty with this particular nanofibers. And also we tested a colorimetric thing with the National Laboratory of Mexico for exact concentrations, and it matches exactly the colorimetric test and what we proved. And apart from this, so they are using fibers in the battery technology also. So they incorporated carbon nanotubes into the polyacrylonitrile, and they use it in the lithium-ion battery, and they get a good charging, discharging, and cooling capacities. So this is one more important application. And then this is for military purpose. So the military people are carrying a lot of things, and they don't want to wear heavy goods, but they want to work in the cold environments, right? So the polymeric nanofibers will be an answer for that. So which is antibacterial, self-cleaning, and lightweight. So they can wear it for many days. And we can able to do super hydrophobic clothing using the nanofibers. You just take the hydrophobic cloth. If you want to wash it, don't wait for laundry. You just put it in the water, soak it, and remove it, and then go to office. So this is a thing which we have in our laboratory. Now, this is the first part where it is concerned with the water purification system. So the second part, what I am going to talk is hydrogen production and environmental remediation. So here we are using a material which is known as graphitic carbon nitride. So it's not an inorganic material. It's an organic material. It's a heterocyclic material, a heterocyclic polymer. So which is having a band gap. That's a good thing, good sign, and which is earth abundant and which is having a good chemical stability and good thermal stability too. So we can play with this. But before going to talk something about how this graphic carbon nitride is going to give a good efficiency in producing the hydrogen, before that, I just start with the work which was done in 1972 by Fujishima and Honda, who were the pioneers in splitting the water and getting the hydrogen. So actually, what they did, they prepared an electrochemical cell where one electrode was coated with the titanium oxide, and other was a platinum electrode, and they exposed the titanium oxide to UV visible radiation. And then what happened? They find some current flowing into this voltmeter, and then they find some oxygen is being liberated at the platinum. So then they got excited and they tried to see what exactly is happening. So after exciting with UV visible, the band gap of titanium oxide lies somewhere around 3.2 electron hole. So the electron hole is formed, and this whatever the holes formed, it oxidizes the water to oxygen and two hydrogen electrons, and the platinum collected the electrons and converted it back to the hydrogen. So this is the first experiment which was conducted by Fukushima and Honda, for the production of hydrogen. And later, the same group, they did conversion of carbon dioxide, which is a problematic thing for us. They converting the carbon dioxide into fuel, converting the carbon dioxide into formic acid, converting the carbon dioxide into formaldehyde, converting the carbon dioxide into methane. So this particular test was taken by the same group, once again using titanium oxide and variety of semiconductors. But here you want to notice here, when they expose this titanium oxide in visible light region, there is no production of products. It's zero. It's zero. In sense, this photocatalyst is only for like you want to use radiations to create electron hole pairs. But our interest is to design visible light responsive photocatalyst. So it is very, very important, and 40% of the fraction of visible light is there in our solar spectrum. So how to utilize it effectively? So the last band gap of 3.2 electron volt of titanium oxide, the researchers think that okay, every time we want to expose it to visible light, but we have plenty of light like sunlight. So how to use sunlight and how to create electron hole pairs, and then later with lot of research gone, and now the use of graphitic carbon nitride, which is a metal-free photocatalyst, is being used for this photosynthesis application. So what is the good thing with GC3N4? It is earth abundant, and it is very simple to fabricate this particular GC3N4, and you can use simple, very cheap chemicals like melamine, dicyanamide, which is rich in carbon and nitrogen, in order to prepare this two-dimensional polymeric graphitic carbon nitride, which is having a band gap in the visible region. So you just take any one of these precursors, either melamine, cyanamide, dicyanamide, urea, or 5-urea, you just heat it more than 500 degrees. And why 500 degrees? This is based on the TJDT experiments, and you can get the polymeric graphitic carbon nitride. Before talking about polymeric graphitic carbon nitride, this was not a new material. It was discovered in 1834 by Liebig. So he just did the thermolysis of mercury thiocyanate, and he found these components, and which one among them is the graphitic carbon nitride. But 10 years before, the boom of GC3N4 started in the field of hydrogen production. So the very first experiment by Vandical, and it is not right to say Vandical, Marcus Antonetti, who is from Max Planck Institute, is a pioneer in, and we can say he is the godfather who did this particular materials to bring into photocatalysis system. So actually, we have different types of GC3N4. The one which is having S triagens, they are more stable when compared to that of triagen systems. So we can able to synthesize. There are many different ways to synthesize, starting from cyanamide, thiourea, and urea. But whatever the material you are going to take, in between you are encountering the same melamine. So it is very easy to do the synthetic process with melamine. You just take melamine and you just do thermal polymerization, and you will get the graphitic carbon nitride. But there are a lot of modifications on graphitic carbon nitride. If it is fine graphitic carbon nitride with the surface which is not porous, what will happen? Visible light come and many reflections will be there. So then they thought it's not my work actually. They created the pores onto this layers. So this is a closed packed layer. This is a closed packed layer, and we can exfoliate it to get the monolayers also. So what happened here? They during the process of this thermal polymerization, they introduced a few droplets of water, which creates the soft bubbles by ammonium and carbon dioxide, which is being released, and it forms a porous units on the surface, which they call it as honeycomb surface. So what is the importance of this? The visible light reflections will be more. So it will be good for photocatalysis. That's the concept. And it is always better to exfoliate. Why? Because if the bulk GC3N4 is a close packed system of many layers of C3N4, which is similar to that of graphite. But if you are going to do the thermal oxidation exfoliation, just heat this at different temperatures, you can end up with nano layers. So what exactly happening during the thermal oxidation? So the hydrogen bond coherent strands or polymeric metals, they are highly unstable against the aerial oxidation. So what will happen? It will break and we can end up with a single polymeric layers. So this is the actual experimental results what we got from this recent publication. If you look at here, the bulk graphitic carbon nitride looks something like rock in the scanning electron microscopic image. But if you do thermal exfoliation of the same, you can see the beautiful single layer of GC3N4, and it is very difficult to view in SEM, but I killed my technician to do that. So, and we have graphitic carbon nitride, bulk, and exfoliator for 450 degrees or 1.5 hours, and this is exfoliator for more time. And if you look at the transition in the material, the one, this is bulk and this is exfoliated, but they are same material. If you look at the surface area of this using the N2 adsorption isotherms, this is GC3N4. The black one is GC3N4, and if you look at the absorption capacities of the exfoliated one, it went up. See here, the surface area here for bulk GC3N4 is 18.9, but the exfoliated one is just 20 times higher than what the bulk is having. And it is having a good band gap compared to the top TaO2. It is having 3.2 electron volts, and GC3N4 is having 2.7 electron volts, which is a good visible light photocatalyst. Now, how the photocatalysis of GC3N4 will help in producing the hydrogen? So, if you excite this GC3N4 with an energy which is higher than or equal to the band gap of the particular material, electron hole pair formation will take place. But at the same time, what will happen? There will be one more thing, that is the electron hole pairs, they recombine back. So before this electron hole pairs reaches the surface and let the electron hole pairs do some reduction and oxidation, before the happening of reduction and oxidation reaction, what is happening? The surface recombination or volume recombination is taking place, and finally the entire efficiency of photocatalytic reactions are being reduced. So it's a biggest problem. As such, we are using GC3N4 for the photocatalysis. So what next? So we started preparing heterojunctions with GC3N4. So here there are three types of heterojunctions. We just do a heterojunction where the conduction band potential of semiconductor 1 and conduction band potential of semiconductor 2 is less, and valency band potential is little less than that of valency band in the semiconductor 2. So this is called type 1 heterojunction, which looks something like this. And then we just go with the type 2 heterojunctions where conduction band is having a little negative potential and the valence band is having a little higher potential, and the charge transfer also changes here. And the third one, both the band gaps don't have any match, that is type 3 heterojunction. So before forming a heterojunction, we should have a good grip on what type of heterojunctions we are going to do. So the required potential in order to generate either hydrogen or to convert carbon dioxide into respective solar fuels, we need these potentials. If the potential lies less than this conduction band potential and valence band potential, we can't able to use that particular semiconducting heterojunction for hydrogen production. So that's why there's a huge chart here, potential versus normal hydrogen electrode and the redox potential of particular reactions like conversion, reduction and oxidation, conversion of carbon dioxide or production of hydrogen, or some oxidation reactions at pH 7. And what to keep in mind, the pH, with pH the reduction potential changes drastically. So the work pH of the solution is pretty important when we are working on hydrogen production. So keeping this in mind, we should start doing type 1 alignment. So what happens in the type 1 alignment? There will be charge transfer from the highest conduction band to lowest conduction band, and there is charge transfer from the highest valence band to the lowest valence band. And but what is the problem with this is upon irradiation with this type of heterojunctions, what will happen? The photogeneration electron hole pairs occur, resulting in the transfer and accumulation of charge carriers in the single component within the hybrid structure, and no evidence that there is a good control on gas separation in this particular type of heterojunction. So people always believe the second one, the type 2 heterojunctions. What happens? The charge transfer is from the highest conduction band to lowest conduction band, and the transformation of charge from the valence band, that is highest valence band to lowest valence band. So people here believe that there is a good charge separation, and this will be this type of heterojunctions will be after photocatalysis to produce hydrogen. And the third one is right. And recently, the type 2 heterojunction is also facing some problem. The type 2 alignment, the main drawback is when the type 2 alignment, when the charge transfer is taken from highest conduction band to lowest conduction band, what happens? The potential of the conduction band we are reducing. So it is moving from the highest negative potential to lowest negative potential, where there is plenty of chances to minimize the reduction capacities. Plenty of chances to reduce the capacities. Like that, we have seen here. For example, if I am going to make a heterojunction with GC3 and this WO3, for example, this WO3 is having a conduction band valency around 0.4, and for hydrogen production I need minus 0.7. If I am doing this type of heterojunction, the charge transfer from the highest conduction band to lowest conduction band will occur, and it will minimize the opportunities of reduction. So what next? So even type 2 is not working in some cases, so people start reducing just in heterojunctions. So it looks like type 2 semiconductor, but the charge transfer is very different from in this semiconductor. So the conduction band electrons in the semiconductor 2 will travel to the valence band holes of the semiconductor 1. So in this particular semiconductor, what is the good thing is you are not changing the potential of the conduction band, and you are not changing the potential of valence band. So the reduction and oxidation occurs very safely. So no problem with this kind of. And there are two types of just semiconductors where we have a interface conductor for effective transfer of electrons also. So now the Z-screen era is going on for hydrogen production, and the Z-screen then applies when you are taking where the conduction band is very high and the conduction band of other semiconductor is very low. In this case, you want to check whether it is type 2 or Z-screen. So for this, many experiments like double beam photochromatic experiments are there to check this kind of transitions. So it is starting from these kind of heterojunctions and coming to Z-screen heterojunctions. So now we started doing water splitting with this as a type 2 or Z-screen, depending upon the type of heterojunctions what we are going to do. So here, what happens if you subject GC3 and 4 to sunlight? The electron hole pair will form, and at the conduction band, what will happen? Reduction will happen, and at the valence band, the oxidation will happen, and it will result in the formation of hydrogen and oxygen. So, but there is a problem with GC3 and 4. What we try to do, actually, I want to discuss about this person, Marcus Antonietti. He is the godfather for creating this metal-free polymeric catalyst, actually. So this is how graphitic carbon nitride look. He is the first person in 2009. He produced 93 micromolars per hour. That is the first report. That is the first report for splitting hydrogen and water into hydrogen and oxygen using this particular GC3 and 4. But what happens when he is carrying out the experiment? There is a huge fluctuation of only GC3 and 4. There is a huge fluctuation of hydrogen production values, 0.124 micromolar. Then what he did, he deposited with the platinum, and then he found that the accumulation of charges on platinum, and from platinum the reduction reaction is happening very well, and he found 250 micromolars after 75 hours of its test, which is 93 micromolar per hour. So that is the first experiment by Marcus Antonietti from Max Planck Institute of Colloids and Interfaces. So what we did recently, we created a heterojunction with titanium oxide and graphitic carbon nitride, and we deferred the contents of carbon nitride to titanium oxide, and then we just managed to have an intermediate band gap, but it is not into the UV region, but it is not as equal as GC3N4. In between, we got an 2.8 that is good for visible light photocatalysis, and this is the heterojunctions what we found. If you can able to see, this is the GC3N4, and you can able to see the formation of titanium oxide onto the GC3N4, and it's a kind of type 2 heterojunction. If you look at the various compositions of hydrogen, what we did, we got C3N4 to titanium oxide 1:4. Look at the hydrogen production value, that is 1041 micromolar per gram, which is like 200 times higher than what Marcus Antonietti did in 10 years before. So after 8 hours of experiment, we got 8,000 micromolar per gram with the same catalyst. So this was accepted recently in the Ceramic International. So it is in press actually. And we try to compare our results with the recently formed heterojunctions. And there is one guy who did the heterojunction with manganese oxide. He is some 40 microliters higher than us, but we are almost nearing the highest values. But still, we are trying to get with other heterojunctions to get the highest hydrogen production values. And then, as I told you, that we need a platinum on the reduction side to have the collectiveness of electrons and to facilitate the reduction reaction. But the platinum is such a costly metal, and what we thought, we can do a short heterojunction, just take the semiconductor and put the nickel and do a short heterojunction. This is metal semiconductor heterojunction. Then our experiment goes entirely wrong. Instead of forming a heterojunction, we tried something else. But we try to analyze that actually. What happens? It is fine up to immobilization of nickel onto the GC3N4, but after the heat treatment, the phase of GC3N4 entirely gone, and there is a new phase of carbon, which is extremely we don't know what is happening. So then we try to analyze, and once again thanks to our technician Joseva, he told that there is some coastal kind of structures in your material. So then we went through high resolution transmission spectral microscopy. What we noticed is the formation of carbon layers on the nickel, and it is extremely different. And what in our observations, I didn't show the actual XPS or EDS of this particular layers don't have nitrogen. All the nitrogen escaped away, and only have a carbon layer, and the space of carbon layer is very hexagonal, and which is very different from our observations. But anyhow, we got this particular observation and very fine. And since it is having a carbon combinations layer, instead of going for hydrogen production, what we did is we just went for decontaminating an organic contaminant, which is nitrophenol. Nitrophenol is very dangerous. Many of the industries they are producing nitrophenol and just going into the water. And what we did is we just converted the nitrophenol into aminophenol. Aminophenol is a very good reagent in pharmaceutical industries. So the duration of decontaminating is once again very interesting. It is 100 seconds. Very rapid, and we can able to see for recording this spectrum also we want to struggle actually. So what happens within 100 seconds, the peak of this nitrophenol diminishes and aminophenol rises. So then we communicated this to metal chemistry and physics journal. The editor himself asked, "It is 120 seconds. Would you send me the video proof of that?" Then what we did, we once again did the video proof for this, and So actually we did the video proof. This is the nitrophenol with the catalyst what we are having, and you can see plenty of catalyst. That is not plenty, it is 0.5 milligrams. 0.5 milligrams, it is very less. And we just added the sodium borohydride. The time lapse of this particular video is 120 seconds, keep that in mind. So you can able to see the transformation of this particular nitrophenol, which is in yellow color. With 120 seconds, you can see that yellow color disappears and you will get the pure white color solution. So this is the reaction actually what we are trying to do. So converting a nitrophenol into non-toxic aminophenol. So with the time you can able to see the yellow color slowly disappears and then it will convert into colorless, which is aminophenol. So after sending this was accepted recently and it was published in 2020 January, I hope. So in metal chemistry, physics. Yeah, this converted completely into colorless, which indicates the complete conversion of nitrophenol into aminophenol. Now, the future perspective in the field of water contamination of producing the hydrogen. So looking at the future, there is limitless scope of opportunities and challenges present for this blooming research topic, and we are confident that expanding the knowledge of fundamental aspects by a more physical chemistry, accompanied with experimental results, by the joint collaboration with the theoretical. Many of the observations what we are doing, they don't have a theoretical support. If you have a theoretical support, we can go further. Very good. So we need a theoretical perspective to bring new findings in the material science, without doubt. And whatever we are doing, it is of laboratory scale. They are having their own problems to convert them to commercialization level. So we want to take a look and we want to collaborate with the engineers and industries to make it possible to convert into the commercialization levels. So therefore, with more advances in material science and engineering, the bottleneck of energy and environment related subject areas can be addressed for sure. And then following solar energy conversions, so it needs a joint collaborativeness between the chemist, physicists, and the industrialist to make it to the commercial level. Last but not least, with the synergy from all disciplines of research worldwide, including material scientists, physicists, and chemists, it is highly anticipated that objective of accomplishing a clean environment and overcome the crisis of fossil fuel depletion to production of chemical fuels from green photocatalysis is mandatory. And it is not a dream. And if we are just leading to the sustainability, for sure in future, maybe in 5 years, you can see all of us are moving with hydrogen fuel. Thank you very much.